So today we are going to discuss questions on the topic of fifth week, that are random vector and joint distribution. So joint distribution is nothing but distribution of more than two random variables. So till the previous class we discussed that what is the probability density function, probability mass function, cumulative density function for one variable and for the function of that random variable. Now we will discuss about the joint distributions where we are focusing on two or more random variables. Okay, so we will discuss how to compute the joint probability mass function, joint probability density function, and then if we have time, then I will go through some independent random variable problems as well. So this is the first problem. So in this problem we have two discrete type random variables x and y whose joint probability mass function is given as pxy, which is equals to kxy, for x equals to 1 2 3 and for y equals to 1 2 3, and it's 0 otherwise. Now we need to find the value for k. So these joint probability mass function also follows the same properties as the normal probability mass function does. So we can start from this question. So this probability density function, joint probability density function is given as kx comma y, where x is equals to 1 2 3 and y is equals to 1 2 and 3, and it is 0 otherwise. Okay, so now we know that summation for summation over xi's and over yj's for pxi yj is equal to 1. Okay, so we can say that probability for 1 comma 1, because x and y, x is taking value from 1 to 3 and y is also taking value from 1 to 3. So these are possibilities that this is p11 plus p12 plus probability 1 comma 3 plus p21 plus p22 plus p23 3 comma 2. Summation of all these possible probabilities is equal to 1. So now we just need to put these x and y values in this expression, the kxy. So it will come out, this will come out k plus 2k plus 3k, again 2k plus 4k plus 6k plus 3k plus 6k plus 9k, and this is equal to 1. And from here we will get that k is equal to 1 by 36. Okay, so we found the value of k. Now next question is we need to find the probability for the same random variables x and y, where x is varying from 2 to 3 and y is less than 2. Okay, so we need to find the probability where x is varying from 2 to 3 and y is less than equal to 2. So this is nothing but probability of x comma y. So we know this x varies from 1 to 3 and also y varies from 1 to 3. Okay. So now we need to so we can put the values for p x x comma y for x comma y is equal to k x y, and we found the value of k, which is nothing but 1 upon 36. So we can find the probability for the points, all the points, by putting the x and y values in this expression. So is there anything? Okay. So we can find that this probability is 1 by 36, this is 1 by 18, this is 1 by 12. We are just putting the x and y values in this expression. So x is varying from 1 to 3, y is 1 to 3. So for y equal to 1, x is changing 1, 2 and 3. So these are the corresponding probability mass function for the combination 1 comma 1, 1 comma 2, 1 comma 3. Similarly, for 2 comma 1 comma 2, it will be 1 by 18. For 2 comma 2, it will be 1 by 9. For 3 comma 2, it will be 1 by 6. For 1 comma 3, it will be 1 by 12. For 2 comma 3, this will be 1 by 6. And for 3 comma 3, it will be 1 by 4. Now we are asked that probability that x is varying from 2 to 3. So we need to so this is the x varying from 2 to 3. So we are interested in this. Okay, and y is less than 2. So y is less than 2 means we are worried about this section. So so these 4 quantities, so this probability that x varies from 2 to 3 and y varies from 1 is less than 2 is the possibility of these 4 outcomes. Okay, 2 comma 1, 2 comma 2, 3 comma 1, 3 comma 2. So this probability is nothing but summation of 2 comma 1 plus 2 comma 2 plus this is 3 comma 1 and plus probability xy 3 comma 2. So we just need to add these quantities and we will get that this probability is equals to when we sum all these, so it will come out to be, I didn't count, I guess. Also we can count it. This will be 1 by 18 plus 1 by 12 plus 1 by 9 plus 1 by 6. So the denominator we can take 36. This will be 2 plus 3 plus 4 plus 6, 15 by 36. So this expression is equal to this 15 by 36. Okay. Now moving on to the next question. So I hope this question is clear. You don't have any doubt in this. If you have any doubt, please write it in the comment box. Now we will move on to the next question. So this is an interesting question. So here we are supposing that there are two buses A and B which operates on a route. A person arrives at a certain bus stop in this route at time t equals to 0. Now let x and y be the arrival time of buses A and B respectively. Suppose that x and y are independent random variable and density mass function of x and y is given in these two expressions. Now we need to find the probability that bus A will arrive before bus B. Okay, so so we are given that x is the random variable which shows the arrival time of bus A. Y is the random variable showing the arrival time of bus B. We need to find the probability that bus A will arrive before bus B. So this expression is nothing but what this expression will be in the terms of x and y. X is the arrival time of bus A and y is the arrival time of bus B. We need to show what is the probability that bus A will arrive before bus B. This means that y minus x should be greater than 0. This y is the arrival time of bus B and this is arrival time of bus A. So this means that this the x is less than y. So that's why we need to find it converted to that y minus x is greater than 0, or we can write it like this. This y is greater than x, so y minus x should be greater than 0, and we need to find the probability associated with this, where y and x are random variables whose probability mass function, probability density function is given to us. So what are those? So probability density function for x is, it is 1 by 3 where x belongs to 0 to 3 and 0 elsewhere, and fy is 1 by 4 where y belongs to 0 to 4 and it is 0 elsewhere. So now we need to find the probability that y minus x is greater than equal to 0, which means the probability of y is greater than equal to x. We can so now these two are independent random variable. Okay, so so this is independent random variable, so we can so if we need to find the probability joint probability distribution for this, So x and y are independent. Okay. So we can find the joint probability distribution of fxy, which will be nothing but fx into fy. Okay. This is the this is the property for independent random variable. So for independent random variable, joint distribution will nothing but multiplication of the individual probability density function. So now we can easily use this for finding the probability that y minus x is greater than or equal to 0. We just need to integrate our joint probability mass function where y where y is varying from x to 4. So the limit of y is 0 to 4, but here y should be greater than or equal to x. So thereby this y is this limit for y will be from x to 4, and for x it will be from 0 to 3. So we will put this so this is nothing but 1 by 12 dy dx x to 4 and 0 to 3. So this is nothing but y by 12 from x to 4 into dx integrating from 0 to 3. This will come out to be 1 by 3 minus x dx integrating from 0 to 3. So this is nothing but we got it is 1 by 3 minus x dx 0 to 3. So this is 3 by x minus x square by 2 from 0 to 3. This is 1 minus 9 by 2, which is equal to, I am doing something wrong. So this 12 I forgot here. Here it is also 1 by 12. 1 by 12. Here also it is 1 by 12. X by 3. I just start from the scratch. This probability that y minus x is greater than or equal to 0 is nothing but the joint probability function where y is varying from x to 4 and x is varying from 0 to 3. So f x comma y is 1 by 12, okay, where x belongs to 0 to 3 and y belongs to 0 to 4. So this is the fxy. So we will substitute here. So it will be dy dx by 12 x by y limit is from x to 4 and x limit is from 0 to 3. So this is y by 12 x to 4 dx 0 to 3, which is 4 minus x by 12 dx 0 to 3. So this is 4x minus x square by 2, 0 to 3 into 1 by 12. So this comes out to be 12 minus 9 by 2, 15 by 2. This will be 5 by 8. This is 5, this is 4. This comes out to be 5 by 8. So the probability that bus A will arrive before bus B is 5 by 8 for the probability distribution function of x as the given for the probability density function of fx and fy, and when they are independent of each other as well. Okay, so this is how you can use this this idea.
Ma'am,
Yeah.
excuse me.
Yeah.
Can you say how you take the limits for y?
Yeah, sure. So the y minus x is greater than equal to 0. Okay, we need to find the probability for this function where y minus x is greater than 0. So we are finding the probability that y should be greater than equal to x. Okay, and y is varying from 0 to 4. But now whatever will be the value of x, so y will be varying from x to 4. Okay, we want that value of y should be greater than x, because we want the arrival time of bus A is x. So this arrival time of bus A is x, arrival time of bus B is y. We want this y minus x should be greater than 0. We want that x will reach before A, right? So that's why y should be greater than equal to x. Therefore the limit for y is from x to the upper limit of y, and this is nothing but it is equal to 4. So I hope you got the idea.
Okay.
Okay. So this is how you can use these concepts are useful in daily life activities or for planning our bus routes and train routes. Okay, so this is how these concepts are useful in real life problems. So we will now move to the next question. So here this x and y are IID random variables, which is independent identically distributed random variables, where x and y both have the same distribution function. Okay, so here it is given for fx, and for fy it is same. It will be 2e to the power minus 2y if y is greater than 0, and if y is less than 0 it will be 0. So now we are given two functions. One is u equal to x plus y and v equals to x minus y. then we need to find the joint PDF of u and v. Okay, in the previous classes we discussed about how to find the uh, distribution of the functions of random variable. Okay, so I will. So previously we discussed that if there is any function, okay, if there is any function g in terms of y, okay, no, sorry, it is, so it is a random variable, x is a random variable, then we have a function g, some function in terms of this random variable. This is the random variable. This random variable has a probability density function, something like this. Then we showed one property that fx, this can be written as g inverse x into differentiation of g inverse x upon dx. So I think the proof of this is discussed in the lectures, in the NPTEL lectures. So you can go through the proof for this thing. So here in this class we will discuss like how we can apply the same concept for the joint probability distribution. Okay, so like we can go through the proof for this one also. So let's suppose we have this function g in terms of y, or we can write this, there is a function g in terms of y. Okay, now the probability that capital Y is less than y, this is nothing but probability, not like this. So we have a random variable x, it's a random variable, and we have another random variable y, which is function of random variable x. Okay, so we can write this probability capital Y is less than equal to small y. Here we can replace this capital Y from gx less than equal to y, and we can write it as x less than equal to g inverse y. So we have this this is a strictly increasing function and this is a differentiable function. So this is a integrable function. So now this is nothing but this fx varying from 0 to g inverse y. Okay, into dx. So this can be written as from 0 if we are supposing that x is greater than 0. Probability density function of fx integrated to g inverse y. Limit will be restricted to g inverse y. So now we can differentiate it at both sides. We will differentiate this term and differentiate this term with respect to y. Then we will get so by differentiating this LHS, which is p y less than equal to y, this is nothing but probability mass function for y, and when for this is LHS, and our RHS, when we differentiate it, this will become this f of x g inverse y into d upon dy g inverse y. Okay, so this is proved that this fy is equal to this fx g inverse y into dg inverse y upon dy. Okay, but in this in the joint probability distribution we cannot find this thing. So this, in joint probability distribution, this is replaced by Jacobian. Okay, where we all know what is a Jacobian is. Jacobian is nothing for u and w, let's suppose, is determinant of del x differentiating with respect to u, then del x differentiating with respect to w, del y differentiating with respect to w, del y differentiating with respect to u, and del y differentiating with respect to w. So this is the Jacobian which we use in the joint probability distribution function. So this fx or so when we need to find distribution function of two random variables, let's say u and v, so we will here also take v. U and v, then it is nothing but joint probability distribution of x y, where we will insert a function of u comma v, and then taking the Jacobian, the determinant of Jacobian, this value. Okay, so now we will see how to solve that question. So in that question, x is given as a exponential distribution function, which is 2e to the power minus 2x when x is greater than 0, and it is 0 elsewhere. Similarly, I is also 2 to the power minus 2y, 0 elsewhere. U is given as x plus y, and v is given as x minus y. Now we need to write these x and y in function of u and v. So we can see that x is nothing but u plus v by 2, and y is nothing but u minus v by 2. Okay, so now we can find this Jacobian with respect to u and v. So which is del x del u, del x del v, del y del u, and del y del v. Determinant of this, so this is del x by del u, so x is equal to u plus v by 2. So del x by del u, the partial differentiation of this term with respect to x, with respect to u, is nothing but 1 by 2. Similarly, this is also 1 by 2. Del v by del u is also 1 by 2, and del y by del v is minus 1 by 2.
Ma'am, how you wrote it as u plus v by 2?
So this u is x plus y, v is x minus y. So when we
Okay.
add these two
Okay,
terms,
okay.
yeah. So this is this comes out to be minus 1 by 2. Okay, this minus 1 by 4, then minus 1 by 4, this will be minus 1 by 2. Now we found this Jacobian. Now we just need to use, we will just put the values in our expression, which was fxy t inverse u comma w into this Jacobian. So this so x and y are independent identical distribution. Okay, so this joint probability mass function will be nothing but multiplication of individual mass functions. So this is 2e to the power minus 2x, this is 2e to the power minus 2y, so this is 4e to the power minus 2x plus y, right? So you understand till this point, right? That why this joint probability mass function for x and y is this 4e to the power minus 2 x plus y. Okay, so we will now put these x and y in terms of u and w. So this is the joint probability mass function. So here we will put x and y in terms of u and v. So x is u plus v by 2 plus y is u minus v by 2, and then multiplied with the Jacobian. So this is nothing but to the power, this v by 2 and v by 2 are will cancel out, and this will come out to be u multiplied by the Jacobian. So this is 4e to the power minus 2u, and Jacobian was minus 1 by 2, but we are taking this mod of Jacobian, so this will be 1 by 2. So it is e to the 2 into e to the power minus 2u. Okay. So now we will check the limit for u and v. U is x plus y and v is x minus y. X and y, x is greater than 0 and y is greater than 0. So u is always greater than 0, and v so this will varies from minus infinity to infinity. Okay, so this u comma v is nothing but 2e to the power minus 2u when u is greater than 0 and v is varying from minus infinity to infinity and 0 elsewhere. Okay, so this is how you calculate the distribution or cumulative density function or probability density function for the functions of random variable. Okay, for the functions like this u and v, these are the functions of random variable, two random variables. So by using this formula, so the proof is not important, but the like how we use it is important. So you can stick to this formula. So this is important. Okay. So now I hope you understand this problem. Okay. So now we will move to the next question. So here x and y are two dimensional random variables with joint PDF, which is given from this formula. Now we need to find the value for c, and also we need to find the probability that y is less than 3/2 and x is equal to 1. Okay, so so joint probability density function is given as cx x minus y when x varies from 0 to 2 and y varies from x to minus x and 0 elsewhere. So now we know that this fx yx comma y dy dx, where y varies from minus x to x and x varies from 0 to 2, is equal to 1. So we will just put the values. So this will come out to be cx xy minus y square by 2 from minus x to x 0 to 2 dx is x square minus x square by 2 minus x square minus x square by 2. So this is 0 to 2 cx x square minus x square by 2 plus x square by 2 into dx. So these will be cancelled out. So this is 0 to 2 cx cube 2cx cube, right? This will be 2x square into cx, it will be 2cx cube, and this is equal to 1. So this 2cx to the power 4 by 4 varying from 0 to 2 is equal to 1. 2c into this will be 4 into 4 divided by 4. So from here we get that c equals to 1 by 8. Okay, so we solve the first part of question where we need to find the value of c. Okay. Now we will move to the next part of question, which is we need to find the probability that y less than 3 by 2 given that x is equal to 1. Okay, so this is the conditional probability, right? Here this is that x is equal to 1 and y should be less than equal to 3 by 2 given that x is equal to 1. So this can be written as
Excuse me.
yeah.
Previous question, previous answer. Is it necessary to take first integration of y and then the integration of x? Is there any order for that?
No, like here it is that y is varying from minus x to x. That's why I took it this first I took from y.
Okay.
Or you can as well, like here this x is up to 2, so y will vary from minus 2 to 2. So you can do the otherwise as well, that first you integrate x and then you integrate
Take
y.
it limit of y.
Yeah. So
Okay.
that will also work.
Okay.
Yeah. So this is nothing but probability that y is less than 2 given this is the intersection and divided by probability x equal to 1. Okay, so now I will here like want to give a formula with this is the distribution function, joint distribution function when we are given for the conditional probabilities. Like here this we need to will be the distribution for a given value of y. Okay, joint probability distribution for a given value of y. Here we are not worrying about the individual value, right? But here we will this function is for given value of y. Okay, so formula for this is this will be probability density function for x comma y divided by probability mass function of y. Okay, so here we will put the given value. Okay, so so this is nothing but xy. So instead of x I will write 1 comma y dy, where y varies from it is given that y is less than 3 by 2, but we also know that y varies from minus x to x. So x is equal to 1, so y varies from minus 1 to 1. So here we need to find this y is less than 3 by 2. Okay, so y can vary, y will vary only from minus 1 to 1 here. Okay, because x is equal to 1. So y can only vary from minus 1 to 1, but we are asked that y should be less than equal to 3 by 2. Okay, so the intersection of these two is equal to that y varies from 1 to minus 1. right? So this will vary from -1 to 1, and here we can write this this mm, this can be here it will be that probability of x y, given that x is y, and differentiating it with respect to y. So this is also x y 1 comma y dy. Here x is 1, so y will vary from -1 to 1. Okay, so we can see that numerator and denominator are both equal, so this is equal to 1. In this question, if instead of y less than 3 by 2, it was given as y is less than 1 by 2, then our probabilities will change, because here this fx y x 1 comma y, sorry, this 1 comma y dy, here y will vary from -1 to 1 by 2, because we know that y should be less than 1 by 2, and we also know that y varies from x to minus x to x, and x is 1, so y varies from -1 to 1. So intersection of these two will give the range for y from -1 to 1 by 2. So here this will be, numerator will be -1 to 1 by 2, but this denominator where we want this x equal to 1, only this will be valid for denominator. So that will be 1 by 1 comma y dy, where y will range from -1 to 1, because this condition is not there, right? Because here we will only focusing on this only one function, only this function on which this conditional probability is given. Okay, so I hope you understand this part, that why for this so this limit will be -1 to 1. So I will explain this again. We need to find this probability, and this probability is nothing but y should be less than equal to 3 by 2 intersection with x equal to 1, given that probability is x equal to 1. Now we know the joint probability distribution of x and y, okay, which is cx x minus y. Now we can for this probability we can put the value of x equal to 1 in the same expression. So this is c, because this is 1, so c1 minus y dy. Here the range of y will matter, so it is given that y this is 3 by 2, and this is 1 minus 1. So it is, we know that y varies from minus x to x. X is equal to 1. So therefore this y varies from minus 1 to 1 according to this x equal to 1. Right? This x equal to 1, we know that y varies from minus 1 to 1. But there is another condition that y should be less than 3 by 2. So this will give us this portion. So intersection for these two channels are from minus 1 to 1. So that's why the limit here is from minus 1 to 1. And for when we are given that x is equal to 1, so then we can just put the value of 1 here, which will be c1 minus y dy, and y will range only according to this condition, that y will vary from minus x to x. So which is x is 1, so it will vary from minus 1 to 1. Okay, so these two terms are equal, so this is 1. But if this was given that y should be less than 1 by 2 given that x equal to 1, then our probabilities will change, because in that the range of y will be from minus 1 to 1 by 2. Okay, this will be 1 minus y dy, and the denominator range will be from minus 1 to 1, because we have only one condition, which is x equal to 1. But here we have two conditions, that y is less than 1 by 2 and x should be equal to 1, and for this we have only one condition, that x equal to 1. Okay, I hope things are clear. So now we will move to the next question. So we have this x and y, whose jointly continuous random variable, and we are given the probability density function. Now we need to find whether x and y are independent, and we also need to find the probability that x is greater than y. So we know that condition that x and y are independent are that this will be satisfied. If x and y are independent, then equation will hold true. Okay, and we also know that fx is nothing but integrating it for y over whole y, and fy is nothing but integrating this jointly distribution function for dx for whole x. So I want you guys to try this problem for 5 minutes, and then I will discuss this. Just try to solve using this idea. So the question is this: the joint distribution, so I will write it. Joint distribution is given as this. So this is the question, and you need to use these two ideas. So just try to find this. So okay, I will start with this question now. So we will first find this fx, which is nothing but integrating our joint probability distribution uh, for y, and y varies from 0 to infinity. So this is nothing 6 e to the power minus 2x plus 3y into dy. So we can bring these two quantities out, and we will remain with to the power minus 3y dy 0 to infinity 6 e to the power minus 2x, and this will be e to the power minus 3y by minus 3 varying from 0 to infinity. Okay, so this is nothing but, so this when we will put infinity, this will become 0, and when we put this 0, this will become 1, and so this will come out to be 2e to the power minus 2x. Okay, so this will be 0 minus 1 by 3, so that will become positive 1 by 3, and 3 6,
Okay.
6 will be cancelled out with by 3, and this will become 2e to the power minus 2x. Similarly, fy will be fxy integrating with respect to x for a whole x which is varying from 0 to infinity. So similarly for this we will bring these two quantities out and differentiate this from 0 to infinity. This will come out to the 2 e to the power minus 3 into e to the power minus 3y. Now we can see this fxy is 6 e to the power minus 2x plus 3y. Okay, and this fx into fy is 2 e to the power minus 2x into 3 e to the power minus 3y, which is 6 e to the power minus 2x plus 3y. So these both quantities LHS is equal to RHS, therefore x and y are independent. Okay, so this is the sufficient condition for two variables to be independent, that their joint probability is nothing but multiplication of their individual density function. Now our next question is to find the probability that x is greater than y. Okay, this is x is greater than y. So we need to find the probability that x is greater than y. So we know the joint probability distribution, so we can do it using this fxy x comma y dx dy, where x is varying from y to infinity and y is varying from 0 to infinity. Okay, because x is greater than y, so x will vary from y to infinity, and then and y is varying from 0 to infinity, so it is x equal to y and this is y equal to 0 to infinity. Or you can write this as this probability x greater than y, you can write it as this also, x is less than equal to y, and then you can do it in another way, which is dy dx, where y is equal to x to infinity, and this x will sorry y will vary from x to infinity and x will vary from 0 to infinity. Okay, so so I will go through this first expression, where I will first integrate x and then integrate y from y to infinity and 0 to infinity. This is minus 2x plus 3y dx dy, y to infinity 0 to infinity. We will bring these two terms out. I will bring this 6 out, and this e to the power minus 3y out, and integrate this e to the power minus 2x dx from y to infinity, and this will be this. Okay, I hope this is clear so far. So this is nothing but 6 0 to infinity e 3y e to the power minus 2x by minus 2. This is varying from y to infinity dy. This 6 and 2, this will cancel out and this will become 3. e to the power minus 3y. I will put infinity, this will become 0. 0 minus this, there is this minus, so this will be e to the this minus e to the power minus 2y dy. So this is 3 e to the power minus 3y into e to the power minus 2y dy, 0 to infinity. This is 3 e to the power minus 5 dy, 0 to infinity. This will come out to be 3 into e to the power minus 5y divided by minus 5, where y is varying from 0 to infinity. When we put infinity, this term will become 0 minus, this is a minus, when we put 0 this will become 1, this is minus 1 by 5, so we will get 3 by 5. So this is the probability that x is greater than y. Okay. So I hope this is clear. Okay. So we will move on to the next question. So here the random variable x has a range 0, 1, 2 and random variable y has range 1, 2. The joint distribution of x and y is given by following table. We need to find the expectation of x and expectation of y. So here this is x, this is y. Okay. X and y, x varies from 0, 1, 2 and y varies from 1 to 2. These are the joint probability mass function. Okay, for 0, 1, 1, 1, 2, 1, 0, 2, 1, 2 and 2, 2. So this is so we are given there is x and y. X varies from it varies from 0, 1, 2 and y varies from 1 to 2, I guess. 1 to 2. So there are probability mass functions associated with these quantities. So this is 0, 0.2, 0, 0.1, 0, 0.2. This is also 0.2. No, this is 0. So what this is saying that this is x, this is y, and this is our joint probability mass function. Okay. So for this is 0, 1, 2. This is 1, 2. So when x is 0 and y is 1, for this the probability mass function takes the value 0.2. This is 0.2. When this is 0, 2, when the x is 0 and y is 2, for this quantity the value is 0.1. This is 0.1. For 1, 1, for this is 1, for this x equal to 1 and y equals to 1, this value will be 0. For 1 comma 1, the probability mass function is 0. Okay. For 2 comma 1, for this point, this probability mass function is 0.3, which is higher. This is 0.3. Okay. So I hope you are getting a picture that this is x-axis, this is y-axis. So for these we are plotting this probability mass function values. So for 0 comma 1, this is 0.2. For 0 comma 2, this is 0.1. For 2 comma 1, this is 0.3. And similarly we can plot it for other points as well. So this is a, like, I want to give you an idea that what is this table is all about. This is saying that how these two variables will perform jointly. Okay. Now the question is to find the expectation of x and expectation of y. So from here we can find, so we are given this probability mass function, joint probability mass function. We can find the this is probability mass function, joint probability mass function. So this single probability mass function will be nothing but summation over all j from 1 to 2 x yj. Okay, so we will sum all the probabilities. We will take the sum for all the y's for that particular x. For xi, probability, sorry. So this is a discrete function, okay? Because we have this separate value, this is not continuous, this is discrete. So this probability mass function that x is equal to xi is nothing but summation over all j probability, this joint probability mass function for this xi comma summation over all j's, all the y's for that particular x, which means that probability that x is equal to 0 is nothing but joint probability of 0 comma 1 plus joint probability of 0 comma 2, because y is varying from 1 to 2. So this is summation for all the possible values of y for that combination. So 0 comma 1 and 0 comma 2, that will be the probability mass function for point x equal to 0. So this is summation of these two quantities. So this is 0.3, this is 0.2 and this is 0.5. So we can see the sum of all these quantity is 1, right? So the probability mass function for x is that probability that x is equal to 0 is 0.3, probability that x is equal to 1 is 0.2, and probability that x is equal to 2 is 0.5. This is for x, and we can see that summation of all these probability mass function is equal to 1, so we can say this is an authentic PMF. Now Similarly, we can find the probability mass function of y as well, for y equal to 1 and probability that y equal to 2. So from the previous we can see that for y equal to 1 the summation is 0.5 and this summation is also 0.5. So we can say this is 0.5 and this is 0.5. This is probability mass function for y. Now we are asked that what is expectation of x and expectation of y. So this is nothing but summation of x into x xi into p x equal to xi over all i's. So which means 0 into probability that x is equal to 0 plus 1 into probability that x equal to 1 plus 2 into probability that x is equal to 2. So this will be the 0 plus what is the probability that x is equal to 1. From here we can see that this is 0.2. So 1 into 0.2 plus 2 into 0.5. So this is nothing but 1.2. So expectation of x is 1.2. Similarly, expectation of y is 1 into 0.5 plus 2 into 0.5, which is nothing but 1.5. So these are the expectation for x and y. Okay, so I hope this is clear. So now we will move to the next question. So let x and y are random variables which follows a uniform distribution from 0 to 1. Then we need to find the expected value and variance of distance between x and y. What is distance between x and y? What does the sentence means? Distance is nothing but the difference, which is x minus y. So we need to find the expectation for this x minus y and variance for x minus y. Okay, so we can write these two are random, x and y are random variables, are uniform random variable. So this we can take a function we can take u equal to x minus y. So this u is also a random variable and we need to find the expectation of u and variance of u. Okay, so just this is or I think this is not covered in the lectures so far, so we can discuss in the next class. This thing we can discuss in the next class. Okay, so in today's session we talked about the joint probability problems related to joint probability distributions for both continuous and discrete. So all these questions which I discussed, this is a very important question because we discussed here about this conditional probability, that how to solve it for the conditional probability, the joint probabilities distribution, how, and when they are asking for this conditional thing, then how to solve these questions. Then we also discuss about how to find the distribution function of the functions of two random variables. Okay, this we also discuss. Then we discuss how real life problems can be interpreted. This is an illustration of a real life problems where we can use the concept of random variables, two or more random variables. This was the basic question. Okay, so try to again go through all these questions, and we will discuss this question in the next class, because I think that this will needs the professor will cover this concept in the next session, next week, so we will discuss it then. So try to go through all these questions once again, and if you have any problem, we can discuss in the next class, or feel free to discuss it in the next class. So for now I am ending this session. If you have any doubt, we can discuss that. Nitya, I think you are the only person in the session.
Ma'am, today's session is okay. Thank you.
Okay, sure. Okay.